Good afternoon. Our Sun is a very ordinary, typical G2V type star, which have lived almost half of its pre-main sequence life of about 4.5 million years. However, while our Sun and its planet Sun is a very ordinary star, the planetary system that it hosts is very special to host a living planet Earth on it. The grand architecture of our solar system is established in the first few million years, which in principle seals the fate of the planetary system for its entire life. Therefore, it is very critical to understand and know the first few million years during which the major cataclysmic events takes place, which actually determine whether there will be uh, a planet uh, which will host life at its later evolution. So while there are several important questions that still need to be answered at the first order, one of the key questions about the solar system is what was the magnetic and the flare evolution of the sun? So in principle, we want to know what was the evolutionary history and dynamics of the nascent sun, to know at what frequency, for what duration, and what was the maximum solar intensity during the primeval stage. A major advancement in this particular area was achieved in 2019 when we showed for the first time by by elucidating by illustrating unambiguously the presence of 7 beryllium, a short-lived now extinct radionuclide that has got half-life of just 53 days. By showing its presence in a calcium aluminum rich inclusion, which is one of the first forming solids of the solar system, we could establish that 7 beryllium should have been produced by the local irradiation, meaning by the interaction of solar energetic particle with the gas and dust present in the solar gas and dust present at that time. And because the CI had formed about 0.5 million years later than the canonical time, fiducial time of formation of the solar system, we inferred that the intensity of irradiation at this later stage of time was pretty high, and this work was published in the Nature Astronomy. However, since the CI had formed about 0.5 million years later, we could only infer possibilities of existence of multiple episodes of formation, the intensity and frequency of which at the birth of the solar system could not be very clearly stated. So how do we typically do that? We typically do that by studying what are called as short-lived now extinct radionuclides. Isotopic evidences uh, in meteorites provide evidences of presence of several short-lived now extinct radionuclides, which were extant during the early solar system but are extinct today. Some of these are listed over here, where you can see there's a short-lived radionuclide 41 calcium, which decays to its daughter nuclide 41 potassium in a half-life of 0.1 million years. The inferred canonical abundance at the start of solar system is inferred to be 4.5 times 10 to the power minus 9. The two specific nuclides that we'll be talking today are 10 beryllium and 7 beryllium. 10 beryllium decays to 10 boron. It has got half-life of 1.387 million years, while 7 beryllium has got an extremely short life of just 53 days. It decays to 7 lithium, and as we showed in the previous slide, that's its canonical value. So these short-lived radionuclides can be produced by several sources, and therefore they are traces of those particular sources. In particular, 7 beryllium and 10 beryllium, which was initially for a long time was hypothesized to be produced only by radiation, has been shown that it can also be produced by supernova, and therefore 7 beryllium and 10 beryllium can be produced both by supernova as well as the irradiation or spallation reactions taking place in the early solar system. The short half-life of 7 beryllium actually makes it a very interesting nuclide because its half-life severely constrains its possibilities and source region uh, to have taken place in a very short period of time. So what do we typically do? So supposedly 7 beryllium was produced and it got incorporated into an early solar system solid. Then 7 beryllium over a period of time would decay into 7 lithium. So 7 lithium today in that particular object which incorporated 7 beryllium at the time of its formation would be equal to 7 lithium which was present initially plus the 7 lithium which came from the radiogenic decay of 7 beryllium. So this can be converted into a linear equation of this type. 7 lithium by a stable nuclide of that particular element, say 6 lithium over here, um, which doesn't have a radiogenic um, source. So 7 lithium by 6 lithium measured today would be equal to 7 lithium by 6 lithium which was present initially plus 7 beryllium by 9 beryllium multiplied by the 9 beryllium by 6 lithium ratio that can be measured today. So if we can, so we can measure 9 beryllium by 6 lithium and 7 lithium by 6 lithium in a particular object in a set of mineral phases in that particular uh, forming object. Then the intercept will give us what was the initial 7 lithium by 6 lithium and what was the initial abundance which will be reflected in terms of the slope of the plot between 7 lithium by 6 lithium plotted on y-axis versus 9 beryllium by 6 lithium plotted on the 9 beryllium by 6 lithium plotted on the x-axis. Typically, such excesses are very small and therefore they are expressed with reference to a standard value, typically terrestrial, and the deviation parts per thousand is usually called per mil, and the deviation is expressed in parts per thousand, which is called per mil. The same can be said about 10 beryllium, which decays to 10 boron, and therefore we can have a linear relationship of this kind by measuring 7 beryllium by measuring 10 beryllium by 11 beryllium and 9 beryllium by 11 beryllium in a set of minerals within an object, say a CI. We can infer the what was the initial 10 beryllium by 9 beryllium at the time of formation of the CI, and what was the initial 10 beryllium by 9 by 11 10 beryllium by 11 beryllium 10 uh, 10 beryllium by 10 boron by 11 boron composition at the start of the formation of that object. So to be able to answer that question about uh, the intensity, frequency, and duration of irradiation at the early solar system, we very selectively chose an object which had formed at time t equals to 0, which was very pristine and had several features which could help us uh, derive or help us get this information about the solar system. So we selected a CI from Vigrano, which is one of the pristine meteorites in our collection. This CI had been previously studied for aluminium magnesium, from which we had, from a high precision aluminium magnesium, we had inferred that the 26 by 27 26 aluminum by 27 aluminium in this CI at summit formation was 4.9 times 10 to power minus 5, which would typically, which when inferred in terms of time would mean that this object had formed at about 7.5 plus minus 8.4 times 10 to power minus 4 years uh, at this at the start of the solar system. So this CI is a typical type 2 is a typical type B CI and several features. It consists primarily of melilite and spinel. The abundance of magnesium tends to increase as we move from outside to inside, which the mineralogy and petrography of these minerals allow us to infer its petrogenesis, which is that it had formed in a multi-stage thermal evolution. It has crystallized from a type B melt, where the melt was heated at about 1420 degrees Celsius for an extended duration of time, and then it cooled off at about 0.5 degrees Celsius per hour. Uh, very high precision in situ isotopic analysis were made, which was shown in the previous slide, from which we could infer its time of formation. So for this particular CI, we carried out both 7 beryllium and 10 beryllium isotopic studies, and from this study, we could find out that this CI shows the presence of 7 beryllium by 9 beryllium at the level of 4.3 plus minus 3.5 times 10 to power minus 3. So a range of 9 beryllium by 6 beryllium, um, all within the mellites could be found, and a very well resolved excesses in several points could be observed, from which we could derive this value of the isochron. Similarly, for 10 beryllium 10 boron isochron, we obtained a value of 1.4 times 10 to power minus 2 um, for this particular CI. So once we have these two CI, we could model the production of these two nuclides by considering a solar composition and the spectra of irradiation, so spectra of particles of irradiation to be gamma equals to -2. From this plot, we can see that both 7 beryllium, which is shown by an horizontal line, as well as 10 beryllium, which is shown by this green line, can be produced within within a duration of about a year. Simultaneously, the other nuclides can also be produced. So therefore, then previously, a few other CIs had also been previously studied for their 10 beryllium and 7 beryllium isotopic records. However, one critical thing about these for elucidating the records of 7 beryllium is that cosmogenic effects tends to overshadow or subsume the original 7 beryllium records, and therefore the values that we obtained for 7 lithium by 6 lithium, they need to be corrected for the cosmogenic exposure that those particular meteorites have seen. In these two particular in the two CIs that we have studied, we have done the cosmogenic correction to obtain these values. But these cosmogenic corrections were not done for other CIs, which we did for the first time, and then we have plotted the 7 beryllium by 9 beryllium as well as 26 aluminum by 27 aluminum for a series of objects. The one that we have analyzed in this particular study, and that formed at time t equals to 0, the one we had analyzed previously, and the other objects. So from these, similarly, 10 beryllium by 9 beryllium for these objects have also been known. The one that we studied this time is shown over here. The other one, which we had studied previously, is here. And for these objects, 10 beryllium by 9 beryllium was previously known. So from these two plots, what we can see is that the values of 7 beryllium by 9 beryllium in these objects, and also the value of 10 beryllium by 9 beryllium in these objects span a range of values differing by a few orders of magnitude, which would mean that the intensity, because 7 beryllium has a half-life of just 53 days, so the radionuclide need to be produced within a very short period of time and be incorporated within an object within a year's time, and therefore the object should have achieved its isotopic closure within a year's time. So the intensity of radiation to produce these nuclides should have varied by a few orders of magnitude to be able to produce those nuclides at that level, varying level of a few orders of magnitude, from which uh, uh, we are for the we are able to show for the first time that the intensity of irradiation, intensity of flaring and irradiation from the early solar system varied by a few orders of magnitude during short pulses of time, in short pulses during uh, in pulses in short period of time during the early solar system. And therefore, we are able to confirm for the first time multiple episodes of superflares from sun at the birth of the solar system. So from these studies, we are able to confirm that we are established conclusively that 7 beryllium is present at 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 the level of 4.3 times 10 to power minus 3, which is about 5 times higher than what we had observed previously in the other CI. Because the half-life of 7 beryllium is so small, it should have been produced locally only by the interaction of solar energetic particle with the gas and dust around. Because now we have been able to show it in multiple sets of objects, we can infer that these irradiation events took place at different period of times in in different events, and the intensity of irradiation during these different events were different. The events at the later point of time during class 1 and 2 for the Efremovka E40 that we had shown previously implies that the intensity of irradiation at the later stage was also typically very high compared to what was during, which was before the birth of the solar system. The solar flares at this time should have an X-ray luminosity of about Lx times 10 to power 32 ergs per second, which will produce enough flux of protons per centimeter per second for production of these nucleides. This this high intensity corresponds to 1,000,000 times higher uh, X class flare than what we currently observe. This study also helps us to consider the time period of irradiation, thermal history, and transport of the solids, because for these isotopic records to be produced to be preserved in these objects need to incorporate and uh, and uh, and be stored in a reservoir in which the isotopic closure is achieved and is not further perturbed for next 4.5 billion years. So they need to be transported outwards to a distance of greater than one astronomical unit in a very short period of time of about 1 year. In the end, I will acknowledge my collaborators and my mentors, from whom I had a lot of interaction and be able to had a lot of understanding and um, on this topic from my previous mentors. Thank you very much.